So in the last video, we discussed about the improper integral of the first kind. First kind means in the integral a to b f of x dx, if either a is negative infinity or b is infinity, or both a and b are negative infinity, or a is negative infinity and b is positive infinity. So that means if one of the limit of integration is infinity or negative infinity, or both of the limits of integration are infinities, in that case we can still sometimes find the integral as a finite number. That means if the integral converges, then that integral is finite, right? Or if the integral is finite, then we call it converges. Sometimes it diverges, meaning that the integration will be infinite, and the techniques that we used is, if there is infinity on the top limit or the bottom limit, we call r tends to infinity or negative infinity, and then plug in that r instead of infinity, right? And then you use the technique you learned, and then you finally put back or take that limit r tends to infinity. That's what we did last time. But here what we call is improper integral when there is a discontinuity in the region of integration. What does that mean? That means the function will be infinity, or the function will not be defined when you plug in a in that x, function x, a function of x. In x, if you plug in a, you will get the value of the function infinity, or if you plug in b, you get the value of the function infinity. Or sometimes there will be a point between a and b, a point c between a and b, where f of c is infinity, meaning the f of c is not defined. Okay, that's the case we will see. All right, so how do we handle that kind of problem is the thing. So the first type is suppose you have, let's say, a to b f of x dx, but the function is infinity. If you plug in a in that function directly, then you get infinity there. Or the function f of x is not continuous at the lower limit. So how do I handle this? Is to handle this type of problem, what we do is we do limit r tends to a plus, and then you do r through a, and then f of x dx. That's what you do. Meaning that if the function is not continuous at a, okay, then to find out the limit, we do like this, limit r tends to a plus, because you see that a minus is going to a from below a, but that region does not belong to this a to b. That's why we are going to a from above, that is r tends to a plus. That's what we are using here. Okay, guys. So if the right hand side limit, if this limit exists, if this value is finite, then we call that this limit converges, or this limit exists. Okay, similarly, so here what is happening here is the f of x is continuous in the interval a through b. It is continuous everywhere except at a. In that case, this is how you handle it. Okay. Similarly, if the function is continuous in the interval a to b, including a, but not at b. If the function is discontinuous, here the function was not continuous at a, but here the function, if the function is not continuous at b, but it is continuous everywhere through a through b, including a. In that case, the similar situation, limit r tends to b minus. Why b minus? Tell me why it is b minus. Because You cannot say b plus. B plus will be going to b from above more than b, which is not belongs to this region of integration. So we can go to b from below, right? Because below b are still in that region. That is the region of that. So you can write a through r and then f of x dx. So if this right hand side integral is finite, then we say that this integral converges, otherwise not, right? So what is the scenario here is f of x is continuous in the interval close a and then open b. It is continuous everywhere except at b. Okay, now so how do we figure out if the function is continuous or improper or not? Is you can just plug in the value of, try plugging in the value of a and b directly, and then you will see if one of them makes infinity or not. And there is a third type of that. Suppose f of x is continuous in a to b, but on x equals to c, with c is inside ab. Okay, I should say fx is continuous in the interval a to b, in the closed interval a to b, including the boundary, except on x equals to c, in where c is in the interval ab. If the function is continuous everywhere in the ab interval including the boundary, but not at a point c where c is inside ab. Okay, so in that case, how do you handle that? Is if you have a to b f of x dx, but there is a point c between a and b where the function is infinite or the function is not continuous. In that case, what you do is you break that a to c fx dx and then plus integral c to b fx dx. You see that this function is improper. This integral will be improper. Why? Because the function is not continuous at c. You see that? And this integral is also improper. Why? Because the function is not continuous at c, or the function is infinity at c. This function is infinity at c. Okay, so both of these are improper. Now you use the technique that we mentioned in the first and second point note there. Okay, all right, so this is how we handle this type of problem. Now I want to show you some examples there. Okay, and again, if this limit is finite, we call the integral converse. Okay, if this limit is finite, this integral converges. If this limit is infinite, then the integral diverges. But here, if both of them is, this is finite and this is finite, then we call that the whole integral is finite and converges. If one of them is finite and other is infinite, we call this diverges. Okay, so to be this converge, both of them must be a finite number. Both of them must converge. That's the thing. Okay, now let us do some examples on this type. Okay, let us see an example. So does 0 to 1 over root x dx converge? So is this improper integral first? So what do you think? So there are two types of improper integral. One is one of the limit is infinity. So this is not that type of integral because both of the limits are finite number. Next is we see if one of the limit makes the function infinity. Okay, let's plug in, let's plug in 0. If you plug in 0, you will get 1 over 0. Oh yes, this function is not continued as at x equals to 0, right? Or you see that this value is not defined, it is infinity, right? So here 1 over root x is not continuous. That's the solution. Okay, not continuous at x equals to 0. This is not continuous. okay, because we will get 1 over 0 there. That is the reason. So what we do is we can write 0 to 1 over root x dx is equals to, you can write limit r tends to 0 plus, because we are writing that we are replacing this by r. So I'm writing r tends to 0 plus, because 0 plus meaning we are going to 0 from above 0, that falls in this interval 0 to 1. But you cannot do 0 minus, because 0 minus is below 0, which will be not in this region, okay. And then I can write r through 1. I want to make it simplified form. This is x to the 1/2. I'm moving this to the top, x to the negative 1/2 dx. Does that make sense? Now, how much is this integral? What is the formula for that? Is if you write this limit r tends to 0 plus, right? R tends to 0 plus, and then you can write this as basically x to the negative 1/2 plus 1 over negative 1/2 plus 1, and the limit is r through 1. You see that? So what do you get there then? So you get this much is equals to limit r tends to 0 plus. How much is this? Negative 1/2 plus 1 is positive 1/2. So you get x to the 1/2 over 1/2, and it is r through 1. Does that make sense? Now this is equals to, let me put this, because 1/2 in the denominator, you can write 2 in the front, right? And then write limit r tends to 0 plus. Now you plug in that 1 and r. So it is 1 to the 1/2 minus r to the 1/2, because you just plug in the upper limit and then minus lower limit, right? So what do you get? Now 2 times. So this will be, if you plug in 0 for r, you get 0 to the 1/2. That is root 0, right? Because that will be just basically, this is like 2 times limit and then root x. That's what you get, right? So x to the 1/2 is 1 to the 1/2 is root 1, that is 1, and minus, if you r tends to 0, where does that go? That be 0, right? So that will be 1. Okay, so basically when r tends to 0 plus, this is a finite number. That means it converges, and the value of the limit is basically 2. That's what we get. Okay, so converges, and the limit value, that the 0 to 1 over root x dx is basically 2. Okay, so what does it say? Is basically, if the improper integral is due to the discontinuity at one of the limit, then this is how you do limit r tends to, if the discontinuity is on the lower limit, then you do plus that limit and then plus. If the discontinuity is on the upper limit, then you do that upper limit and then but minus, because it is going through the below, because that below numbers will fall in that region. Okay, that's what you do. So let me take one more example. That does negative 1 through 1 and then 1 over x squared dx converge? That's the question. Okay, now is this improper integral? That's the first question. Is this improper integral? There is no infinity, so we rule out the first type of improper condition. Right now, is the upper limit, if you plug in upper limit in x, is this infinity? No. If you plug in lower limit in x, is this infinity? No. But is there anything between negative 1 and 1, if you plug in here, makes it infinity? Yes, because since x equals to 0 is a point of discontinuity, and x equals to 0 is in the interval negative 1 through 1, the integral is improper. So it is improper, right? Again, the idea to identify the improper integral is first check the limit. If the limit, one of the limit is infinity or both of the limits are infinity, it is improper. Second, check the limit. Although the limits are a finite number, when you plug into the function directly, it may give you infinity. So in that case, that will be improper integral. Or the third type, or the very not clear type, is there may be limits, finite limits, okay, but there may be a number or value of x between those limits somewhere in the middle that makes the function infinity. That is another type of discontinuity. Okay, so the discontinuity may be on the lower limit or upper limit or in between. In that case too, the function is improper. Now, how do I handle this type of integral? That is the thing. Okay, to do this, what we do is we do like solution is, let me use a different color, -1 through 1 over x squared dx. So what is the discontinuity point? That 0, right? So I want to break this into -1 to 0, -1 to 0, 1 over x squared dx, okay, and then plus 0 to positive 1, 1 over x squared dx. That's what I can do, right? Now what I'm going to do here is I'm taking the first integral, okay? Now let's take the first integral, -1 to 0, 1 over x squared dx. So this is improper integral because when you plug in 0 here, you will get 1 over 0. That makes infinity. So you can write limit r tends to 0 minus, but because you cannot go to r tends to 0 plus, because 0 plus will be above 0, which is not in this limit. You see that? Let me do that. Okay, so this will be -1 through what? R, right? And then this 1 over x squared can be written x to the -2 dx. Okay, so let us do that. Limit r tends to 0 minus, what is the integral of that? X to the -2 plus 1 over -2 plus 1. You see that? So what do you get? That implies, and then on -1 through r. Now what do you get there? So you get, this is -2 plus 1 is -1. This value is -1, right? So you can write a -1 times, right? So let me use the same color there. So -1 times limit r tends to 0 minus. 0 minus is basically the 0 here. So you get x to the -2, right? Plus 1 will be -1. So 1 over x, and then the limit of integration are -1 through r. So -1 times, let us plug in the limit. Oh, by the way, I need to write the limit of integration. So limit r tends to 0 minus, right? Plug in that 1 over r minus 1 over -1 will be plus 1, right? You see that? This is what you get. Now plug in the limit. What do you get? If you plug in the limit 0, you will get 1 over 0 is infinity. So it diverges. Since the first piece diverges, it does not matter whether the second piece diverges or converges, because one of the piece diverges means the whole integral diverges. Okay, so that's what you write. Hence -1 through 1 over x squared dx diverges. Because if one of them is divergent, you don't have to check for the other one, because it will still diverge. Okay, that's how it works. So you can, basically there is one formula that you can define here. What that formula, you can definitely prove that formula or by doing the problem. Okay, we call p test, because do you remember that we had a p test if one of the limit is infinity, a through infinity, right? If it was a through infinity, then we call that 1 over x to the p dx converges if p is greater than 1. I will write down here. Let me write down that thing here. If it is like a through infinity 1 over x to the p dx, then this converges if p is greater than 1 and diverges otherwise, right? That's what we learned. But there is a formula for 0 to a also. See, even though it is not infinity, if there is like 0 to a and then 1 over x to the p dx, where a is positive. So where a is positive, okay, in this case also this integral converges if and only if p is less than 1. You see that here our p was greater than 1, that's why it diverges. If this p is less than 1 for 0 to a, you see that for 0 to 1 you can try that 0 to 1. I mean, we did this for the first integral, but you could have tried this one, this integral, instead of trying the first integral, because it is 0 to a is positive, right? And then 1 over x to the p, it diverges because that p is greater than 1. If p is less than 1, then it would converge, okay? That's what you get here. All right, guys? So here also we need a is positive there, right? Because we let me double check that. So I think that p integral test, yes, a is positive. You need a is positive in both cases, right? So we got the two formula that you can use directly. In case of 0 to a, where a is positive, 1 over x to the p dx converges if the p is less than 1. But a to infinity case, where a is positive, 1 over x to the p dx converges if p is greater than 1. In this case, you will need p greater than 1. In this case, you will need p less than 1 to converge, otherwise it diverges. Okay, guys? So this is how you handle the second type of improper integral. Okay, guys? All right.